Welcome everyone. During today's lecture, we are going to discuss one of the most important elements that's related to high voltage safety and protection operation, which is related to earthing system, high voltage earthing system. Also, earthing is used in low voltage as well. Before we start, please allow me to give you a small brief about the relation of earthing and electrical and telecommunication engineers. Earthing system, adequate earthing system is required for safety purpose, operation purpose, for low voltage, high voltage, extra high voltage, transmission line, substations, also telecommunications. It's very critical to have an adequate earthing system for all your communication towers. Earthing system for water pipeline. Earthing system for buildings, for warehouses. So earthing system is required almost on every single infrastructure that has electricity or communication or even pipeline running in the same easement as power line or high voltage system. So this topic is very important. Now, it is not possible for us to cover the entire earthing system in one lecture. So we will divide it through multiple lectures. And I hope you will gain the benefit from it. Let's start. So, during today's lecture, we are going to focus on the soil resistivity. Soil resistivity, it's very important when it comes to your earth grid resistance. Also, direct soil resistivity has direct impact on your allowable safety limit, which is also has direct impact on your setting of your relay for a protection purposes. Let's start lecture number 1 on soil resistivity. During today's lecture, we will give you a quick introduction regarding earthing system, standards. I will focus more on the Australian standard during this. However, in the American standard, in the IEC standard, the European standard, they all have an equivalent standard to these ones. The idea behind the standard is to show you the wide area of engineering that required earthing, an adequate earthing system, which is soil resistivity form its main part, one of its main part. History behind it, soil resistivity test method. Now, we need to obtain an accurate soil resistivity test. I will show you the available method and what you need to do to eliminate or to minimize the error during testing. Next lectures, we will show how can we determine the soil structure using soil resistivity test for our earth grid modeling. Soil resistivity values, learning and discussions. Let's start. What's high voltage earthing system? I'm pretty sure anyone working in the industry, telecommunication, water, electricity, low voltage, medium voltage, high voltage, heard of high voltage earthing system. In some countries, they call it grounding. It's a grounding system in some countries. What is it? Its main role is to establish a low resistance path to absorb the fault energy and return it back to path. Remember what I'm going to say now. The fault current always has to return to the start of where it's generated. Always has to return back to the start where it is generated. Remember this. Never forget this. So I need, under fault current to ground, I need to establish a low resistance path. Why low resistance path? Ohm's law state that the voltage generated or the voltage across a resistance, it's I time R. The fault current, when I introduce a low resistance path at the location of the fault, that means the earth potential rise, EPR, the earth potential rise, will be I multiplied by the resistance, which is the lower the resistance, the lower the earth potential rise. The lower the earth potential rise, lower the risk of me getting electric shock under touch or a step conditions. This is introduce a safe path for fault current. I need to introduce a safe path not only for human, also for equipment. If there's a fault, I don't want the energy, the massive energy of the fault to damage my equipment. I want it to be safe path back to source. As we spoke, ensure safety of the workers, not only the workers. Transmission line, some of the transmission line running across houses, in front of houses, on the street. Also these days, the neighboring rate between substation and residential property increased, especially within cities. Also, in many countries, let's look about, for example, Dubai or Sydney. In the city, there is a substation within the building, or for any big building, they could have multiple substations. Could be 33, could be 33 kilovolt, 11 kilovolt, 22 kilovolt, 66 kilovolt, 500 kilovolt, a indoor substation within major cities. Safety of the public. Because now the high voltage infrastructure, as we spoke, for substation or transmission line in a close proximity to public, I need to make sure under any fault, safety of the public is always maintained. That's very important. I spent a lot of years of my experience working in Sydney, and I know there is a Work Health and Safety Act 2011 that put responsibility on the designer if you don't make sure there is an adequate safety consideration. Adequate protection. For those who studied protection or work in a protection, they know that soil resistivity or earthing system play an important role. Setting of the relay. Based on your fault, if you have a fault at the substation, the fault impedance will be the resistance of the substation. And the magnitude of the current will depend on it. So if you have an overcurrent relay, if you have any type of relays that require earthing system, require reading the resistance, of course, this is play an important role. It's very important for the protection to have an adequate earthing system. Also, there is multiple type of protection, but let's talk about high fault current protection. That means I have low resistance to ensure I have a high fault current. In a mine, for example, they use a fault current limiter by introducing a high resistance on the return path, not the substation earthing. On the star of the transformer, they put could be zigzag transformer, high impedance transformer, to make sure the current, when it comes back, there is a high resistance to reduce the fault. Adequate detection. To detect a fault, the relay is set, depending on some relay setting, depending on the fault current magnitude. The fault current magnitude, let me write to you the sequence component. If I say I0, it's equal to voltage divided by Z0 plus Z positive plus Z negative plus 3Zn. This is related. This is impacted by the earth grid. This is impacted by the earth grid at the fault and the earth grid that connect the star with the transformer. I have a transformer, I have a delta star. This transformer is feeding a substation. In this substation, I have a fault. In this substation, I have an earth grid. This goes. In here, I have an earth grid. This fault that goes into here has to return back to the star. If this was, for example, 0 ohm, and this was 1 ohm, I have to consider this. And these are the sequence components. The fault current is 3I0, which is at later stages. We will do a lecture about how to calculate the fault current into a system. Now, why high voltage earthing system is required? There is no high voltage infrastructure that doesn't have earthing system. There is no building low voltage that doesn't have earthing. There is no building that have a low voltage system or a high voltage system or a mix without having an earthing system. Because as we spoke, I need to control the EPR, the earth potential rise, to provide a return path for fault current, a safe return path for the fault current. For the fault current to be sensed and rapidly disconnected from the system. For those who work into the design of a circuit breaker, of a protection relay, they will understand the importance of this. Depending on your fault magnitude, the relay trip time will change. It's very important to understand primary clearance, secondary clearance time, which is we will discuss it when it comes to human safety, another lecture. To provide a reliable path for earth return, you will see what's SWER, single wire earth return system. We will talk about it soon. So to provide a reliable path for earth return current without generation of significant standing voltages on the earth system. As I spoke, when I have a low resistance, it goes back. Smoother without having a major earth potential rise. Reliable operation of circuit protection devices, we already spoke about it, ensures safety step voltages around high voltage infrastructure. This, we will have one lecture to discuss about safety of a step and touch voltages. We will have an entire lecture to discuss these 2 points, step voltage and high voltage and touch voltage. If you live next to a high voltage infrastructure, or there's a tower or there is a pole in front of you, high voltage pole, under fault condition, your conductive fence, if there is no adequate earthing system, if you touch the fence, you could get electrocuted. Your earthing system will ensure the step and touch voltages is below the allowable safety limit to keep you safe. Structure damage. For example, if you have a transformer, if there is a fault at the bushing and there is an adequate path for the fault using earthing system, you will bypass the energy of the fault. So instead of going inside the transformer and cause damage, you will bypass it. Lightning protection. Lighting protection, the earth grid form a low pass for the lightning energy to be absorbed. There is a YouTube video that I've already uploaded regarding earthing system for lightning protections. Go back, check it, and you will see some information. However, the main role for this earth grid or earthing system for lightning protection is to ensure I have low pass to avoid or eliminate or reduce the risk of a damage and the lightning strike. That's very important when it comes to communication, telecommunication towers. Of course, it's very important also for a substation, transmission line. You don't want the substation, you don't want your transmission line or a substation under lightning strike to lose power. This is very important. Now, standard and regulation. The drive behind these two slides is to show you the large number of standard and regulation that govern the earthing system. I want to show you the impact, that the earthing system impact is wider than one or two standards. Let's go through it. This is an Australian New Zealand standard govern a low voltage installation within a building. This is an overhead line design, Australian and New Zealand standard for overhead line design. Substation and high voltage earthing design. Electric hazard on metallic pipes. Electric installation surface line and association. So look, so far, low voltage, overhead line, substations, metallic pipeline. Metallic pipeline, it's a concrete with a steel reinforced considered also under this standard. Under mining surface, low voltage or high voltage. Telecommunication network. See, this is a telecommunication network. This is for telecommunication network number 2. They had 2 standard. Lightning protection. Power and telecommunication, low frequency interference. AC interference. So let me explain a bit about the AC interference. If you have a transmission line running, could be 50, 100 meters away from you, could be 200, depending on the length of the parallel path. And you have a fence or a telecommunication wire using copper or pilot wire for communication. If they're running in parallel to a certain distance, there is an induced voltage due to AC interference, LFI. Earthing system, it's very important. Earth potential rise. Look, another one for earth potential rise, protection of telecommunication network using personal and plant work example. Another one. New South Wales government, Department of Water and Energy Code of Practice, talk heavily about earthing system. Health Safety Act, Work and Health Safety Act 2011. There's heavily reference to earthing system. Blue Book for Victoria, another state in Australia, Code of Practice of Electrical Safety for works on or near high voltage electric apparatus. Go to another one, standard. By the way, now, this is now changed to 2013. IEEE, grounding for industrial and commercial power system. For direct lightning strike into substations. Protection grounding of power line. Practice grounding potential and used voltage from power fault. This is like an LFI. So, as you can see now, under the Australian banner, there is a large number of standards. By the way, I did not list them all. I listed some of them. Same for the IEEE, I listed only some of them. To show you that the earthing system spread into a wide area. Now, history. I always find this history fascinating. When and how we establish earthing system. You'll be very surprised that the first earthing system is used not for electricity purpose, for communication purpose and the telegraph. Let's go through it. Early 1800s, electric grounding is a direct electric connection to the mass of Earth. In 1820, electromagnetic telegraph system used two wires to communicate the signals and return the current. So they usually, for the communication, they send the signal in one wire, return it, running parallel. This running parallel caused an interference. This interference required additional repeaters, additional station, cost more money, makes it more complex, and high maintenance cost. In 1836, Mr. Carr discovered that the ground can be used as a return path for the circuit. Well, look, 1836, he found. So what he did, he said, hold on a second, the telegraph, why do I need to have a return back? He drove an electrode deep in the ground to establish a low resistance so can send the signal back. So he will send one wire on the signal and then the return will be through the ground. That's made a massive increase in the deployment of the telegraph receivers. Changed the approach completely. And by the way, I read that during the World War, they used this as a very secure communication line because it's very hard for someone to pick up from the ground what's happening. Later, he said, power engineering said, hold on a second. We can use the same. We can send the active power using one line, and the neutral, we will let it return using the ground. Single wire earth return. So instead of having two wires, active and neutral, to go up, so one will send, one will return back the power to close the loop, the circuit. He said, hold on, we can use single wire earth return. And this reduced the cost of the wiring system. And this area, this system is still used until now in a rural area. In the early years of 20th century, they found when they introduced the rotation machine, they find a lot of issues with fires and cause death casualties. After a lot of research, practices for ensuring that electrocution hazard and association, all these meetings, all this investigation resulted from this situation. Grounding and earthing of electric equipment were mandated as a functional use, evolving from the reliance of power fault control and line protection systems on the low impedance earthing connection. Grounding was identified as the ultimate design practice. So the history of earthing first was introduced for the telegraph, then single wire earth return for power delivery, and then for the machinery, when they introduced of the early 20th century, they introduced the electric machine, the rotation machine. From the rotation machine, they found there's a lot of issues. They would go on the fire. There's a lot of electrocution, a lot of casualty. After a lot of investigation, they found when they start connecting the earthing to the body of it and to the neutral of it, depending if it's star delta and is a star earth or not earth, they found the solution, and they found that the safe to us is the earthing. See, our planet gave us shelter and also gave us safety from an electric fault perspective. That's amazing. A good ground is considered an ultimate need. With this, the legacy begins. The legacy of earthing. For those who follow the earthing system, they call it black art. In my personal view, anything it's a black art unless you understand it. When you grasp the foundation properly, everything will be very easy. Now, today we are going to talk about IEEE 81 standard, which is regarding to the soil resistivity. There is also IEEE 80 that uses the soil structure from IEEE 81 and then deploy it for earthing system. Soil resistivity testing is a process. Now, I need to measure the soil conductivity, the soil resistivity of the surrounding ground. Soil resistivity testing is I am testing is a process of measuring the conductivity of the soil. So I need to make sure, is my soil surround has low ohm per meter or high ohm per meter? If high ohm per meter, I need a complex earthing system design. If it's low, it's very easy to achieve my desired resistance. So let's look at it. It's very important, guys. It's very, very important to understand. It's very important, guys, to understand. It's very critical that the soil resistivity vary when you have type, temperature, moisture, mineral contents, and compactness. So whenever I go ahead and I measure a soil resistivity, it's very important for me to note the type of soil I measured and also the condition I measured under. Was it wet condition? Was it dry condition? Humid? All this information, as you will see, play an important role. Look, this shows the moisture. How does the moisture reduce the resistivity? Salt reduce it. Temperature also. Can you see under ice? Have a very high resistivity. It's very important to note this. Very important. For the temperature, usually the tests happen in maybe the test you do at daytime maybe happen around here. So if your area goes under goes under icy stage, look the difference. Look between this point. Let's look, I have tested it at 30 degrees. And then suddenly it goes down to 0. Look, 10, 100. If it goes down to minus 10, 1,000. So see, it's big changes in the same soil that I tested. Now, you have to keep in mind one element, which is very important, is the weather will affect the surface, or also can it affect the electrode that goes down deep in the ground. So for example, this temperature, can it affect half a meter below ground, 1 meter below ground, 2 meters below ground, 10 meters below ground? All this play an important role. But this surface, definitely the temperature have major impact on the surface, which also impact your allowable safety limit. You will see. Method of measuring. Now, after we establish the ground of importance of our earth grid, I need to measure the process of my earth grid system. I need to measure soil resistivity to be able to determine the size of my grid that give me low resistance. Next lecture, we will show you how to design an earth grid using the measured soil resistivity. 3-point test. The ground resistance measured are repeated several times in correlation with the ground rod increment increase in depth. 4-point. So I have a 3-point method. I have a 4-point method, which is we're going to go through each step. 4-point method, a good method for measuring the apparent resistivity for a large volume of undisturbed earth is the 4-point method. 4-point method, Wenner and Schlumberger array method. These two methods use 4-point, and then you have a driven rod method that use 3-point. So let's look at the first one. So the machine drive down 2 probes to measure the voltage, and then 2 probes to measure the current. The separation between each probe are equal. That's known as Wenner method. 4 probe. 4-point. 1, 2, 3, 4. And if you go through the IEEE standard or Australian standard, at the end, the equations, because remember, you are measuring a huge area. You are measuring, if I go back, you are measuring, see this B? This area A, this B maybe is 5 centimeters, 0.5. You know? 0.05. Could be small, 2 centimeters. A will be in meters for substations. At least you will see now. It could be maybe give and takes 100 meters, 50 meters, depending on the site. So 50 meters, and this is very small. So if I go back and I apply large against very small, this 0.05, 0.02, and this could be 150 squared. So therefore, I can have an estimated, very accurate one, that the soil resistivity using Wenner method is 2 pi AR. 2 pi AR. R, I remember I'm measuring the voltage and measuring the current. The resistance is V divided by R. I use Ohm's law. So the machine has an internal algorithm. I separate them as I showed you using A separation, exactly the same. And the machine automatically will measure the voltage, measure the current, automatically will give you the value of the resistance, and then you can program the machine to use this by giving it B, or use this equation. This equation, it's give you very, very accurate reading when it comes to large system. Also for a small system, you will see it's always you have to have at least a few meters. And this B will never go down, maybe 5 centimeters, that much, maybe 10 centimeters if you want. This is the Wenner method. That's the Wenner method. Voltage and a current probe. Current, measuring, and you're measuring the voltages. And in theory, if you have one layer of soil, in theory, you are measuring a distance down. That's why, by making this bigger, larger, in reality, I'm going down into the ground deeper. You can use this method to determine the type of layers underground. And if you have a very, very sophisticated machine, it will give you very good, accurate result for the bottom area. So, recommendation. To go ahead and to measure a system, I note where's the location I did, and then I measure these two. I write down whatever the machine gives me. Because at the end, I can compare if there's any mistake. I write whatever R, whatever rho. I put them down. And look, as you can space probing, look. I'm reaching 16, 22 meters, 120 meters. This system in here, remember, 8 meters, A squared, and I have B is 5 centimeters. It's always very large. A always very, very large in comparison to B. Now, Schlumberger array. Schlumberger array, it has a 4-point. However, I can put this 2 probe far away, and then I measure the distance L, and that's from the center same, and then I changes small l to suit. I change it small l to suit. So in Wenner array, I have to always change the 4 probe. Every time I want to take a new measurement, I have to take 4 probe, change them. For Schlumberger array, I don't have to. I can set these 2 external ones and then start moving the 2 internal ones. Now, this is the equation. This is a big L, pi. The soil resistivity is pi, big L, which is this L, R divided by 2 small l. where the distance. Schlumberger and array method array. This is a comparison between the two. Let's check what's the difference. Schlumberger array method. This method is supplementary economical than the Wenner when it comes to the manpower. Of course. In a Wenner, all the time I need to change the 4 probe. In Schlumberger, I only change 2 probe. I can fix the 2 on the side and then start changing 2. So of course, required less manpower. The outer electrode can be moved 4 or 5 times. This is what we spoke. When contact resistance, check about the Schlumberger array. When contact resistance, the resistance of the top layer of the ground is very high, this can lead to an error in the reading of the machine during the soil resistivity test. It's very important. If I'm using Schlumberger array and I have an asphalt, for example, or a sandy area on top, I have a percentage error. I could have a high error when it comes to reading during the soil resistivity test. The machine has maximum loop impedance. In some cases where the soil resistivity of the top layer is very high will lead to a loop impedance higher than the maximum loop impedance of the machine. That's the reason. Every machine has a loop impedance. If I have a very high soil resistivity, I exceed the loop impedance, which is lead to an error in reading. In this case, you can use the reciprocity theorem, inverse Schlumberger array. I can tell you, based on my 13 years experience in the field, the most commonly used one is Wenner array. Now, 3-point method. The 3-point method is I drive an electrode down and measure the distance. By keep driving it down, I have this equation. This drive down, I keep changing L, drive down. And then I'm measuring rho. This method requires big machine to keep driving down. If you want to drive something 10 meters, you could have a rocky area at the bottom. You need a big machine to drive, and every time you drive, you have to measure. This method, it's good in one thing. It will give you an indication on the bottom layer. Is it solid layer, rocky layer? If you have a very rocky or a solid layer, maybe you choose to do your earth grid horizontal instead of vertical. This would give you an indication. However, costs a lot of money. The 3 method when it comes to soil testing. These 3 methods. Now, Ohio State University demonstrated that either the Wenner 4-pin or the driven rod method can provide the information needed to develop a soil model. Like I said, under separate lecture, we'll talk about soil model. So now it's being proven, and it's evidence that I can use either Wenner or a driven rod. These 2 will give me my sufficient information to establish an adequate soil structure. The Wenner method, as I told you, is the most popular one due to the following reason. Wenner method is capable to obtain data from a deeper layer. Remember, Wenner method goes down deeper layer. Okay, it doesn't go depending on the structure of the soil, but it will keep going deeper. So you go further up, it will go deeper. No heavy equipment is required to perform the test. I will show you a machine that big, capable of producing the test. Have a circuit that keep injecting current from a battery until have a continuous steady state current and do the measurement. The results are not greatly affected by the resistance of the test point. Are not at all. The results are not affected by the hole created by the driven test point pin. Remember, when you have a driven electrode down, you have a big machine driving the electrode down if you want to go down for 10 meters or 15 meters. One advantage, as I told you before, one advantage can be drawn from the driven rod method, the ability to determine to what depth the ground electrode can be driven without facing any solid ground. That's it. That's the advantages. That's it. but costs a lot of money. Driven rod, you have to use it. If you have a crowded city where there is no sufficient area to do the Wenner method this way, then you will be forced to drive down. You have no choice. Based on IEEE 81, Wenner method, space probing and error range. Guys, look. Probe spacing percentage of the grid length. If you do the probe spacing is 40%, look the error. Touch and step voltage error. If you do it 300%, what does mean 300%? I have a grid size. This is my grid size. My grid is 50 meters. I need to have A. Remember this? This A has to be 300%, which is 150 meters. 150 meters. 150 meters. So I need an area. If I have a grid of 50 meters, I need an area, direct line of 450 meters. It's not possible for me to find this in the middle of the city. That's why I will be forced to drive down. So this will give you, if you're a project manager, if you are a project manager and your consultant or your engineer, you are in an open area and your engineer gave you a soil resistivity test or an earthing system with a soil resistivity test where they did an A, this is 50, they did an A of 20, so they did an A of 20 meters, you can tell them, guys, there will be high error. If you did 100%, still, you should ask him to do it 300%, at least go 3 times more to make sure there is no error. So I strongly recommend, in an open area where it is possible, ask him to do 300%. I put this value to give you a typical resistivity value. Seawater, it's between this limit, typical ones. Range, look at the ice. Water, see, look at the ice. Keep this information handy because our next lecture, when it comes to allowable safety limit, depend on this. This table shows the moisture. This is in a clay mixed with sand or a sand. Look, when the moisture changes, look what will happen. Let's end now our first session. So in this session, you saw the importance of earthing system. And part of the earthing system, soil resistivity formed the main element. To measure the soil resistivity, there is 4 or 3 methods we discussed. We did not discuss, only discussed 3 methods. Wenner, Schlumberger, driven rod. The most commonly used one, Wenner, driven rod. These 2, if you use one of them properly, can give you the desired reading. When it comes to Wenner, the most used one, we provided you with a table regarding to the A, the desired A in respect of your length of your substation earth grid regarding the error. Also, we showed you the moisture and temperature. It's very critical to take into consideration the weather condition when you do your test. I hope that's clear. Now, during our next session, or next lecture, we are going to take this measured soil resistivity from the table. Remember when we showed you the table, there's a lot of A, and how to use IEEE 80 standard to establish a soil structure for us to use for allowable safety limit determination, and then for your earth grid determination, and then for your earth grid resistance calculation, and then for your step and touch voltage calculations under fault condition. I hope that's clear. Thank you for listening, and inshallah I'll see you safe next time.